Great. So, yeah, I think.
I'm just puzzled about point 2 because presumably diffuse means that the center has no common part. There's no direct, there's no factor direct sum, no minimal direct sum.
Okay. So I'm saying that I'm not saying the center is diffuse. I'm saying the algebra itself is diffuse.
Well, so I wonder, I'm not quite sure if I'm familiar with the term diffuse for anyone else.
So diffuse means it has no minimal projection.
Oh, right, okay, so it's so the center is diffuse and also it's
No. The center is not diffuse. The center might be trivial. The center might just be the complex numbers. But the algebra itself doesn't have any minimal projections. This doesn't, I didn't say anything about the center. Yeah.
no.
Okay.
I didn't mean to say that.
Okay. So now that you asked the question about that statement, how about I actually like present the statement itself?
I think it's like one. I mean,
all of these are spatial with spatial states. So all is type 2.
It says it has no type 1 factor direct sum.
Sure. Yes. That's true.
But isn't that going to be true if it's true for n1 and n2? Isn't it going to be true for the tensor product?
Yeah, the tensor product will be diffuse. But diffuse doesn't imply that H equals 0, right? Like free group algebra is diffuse and H is infinite.
So that's not enough for the entropy to be negative.
Yeah, so the main point in here is tensor product.
Yes, but
and making them diffuse is just sort of saying it's, that we're not in a trivial situation.
Okay.
Stuff that is not diffuse we don't really care about in this study. So the main point is a tensor product and in fact commutative. Okay, so now that we've spent like a couple minutes answering questions about the statement, now I'm going to tell you the statement. So first of all, so this is similar to the ones I did before. It can be deduced from these properties. If you have the commutant of n inside of M is diffuse, meaning it has no minimal projections, then this H of n in the presence of M is 0, and then also the H of a tensor product is 0. So these are also basic examples, and then after this I'll tell you something, another an application of this philosophy as well. So here, okay, so if n intersect n, or if the n commutant intersect M is diffuse, then there exists some A diffuse abelian, which is contained inside this here. A inside n prime intersect M. And so then what we say is, well, okay, so this n is then contained inside the commutant of A, and the commutant of A is inside the normalizer. Of A. And so then you apply the monotonicity property and say, well, H of n in the presence of M is less than or equal to H of the normalizer of A, the von Neumann algebra of the normalizer. And that's H of A in the presence of M, and then A is abelian, so then this is less than or equal to 0. Yeah, so if you have diffuse stuff which commutes with you, then that means that you can't have that many matrix approximations. And at root, I mean, if you think about this property, this is already present in Wojciechowski's paper, and in fact also in von Neumann's paper about generic choices of matrices and trying to solve problems with commutators of those. And the idea is, yeah, if you pick something in the matrix algebra which has diffuse spectrum, right, then you could imagine you could assume it's diagonalized. So say assume it's self-adjoint and is diagonalized, right? And then things that commute with that are going to basically, the commutant of a diagonal subalgebra in matrices is a diagonal subalgebra, but also if you're close to commuting with the diagonal subalgebra, then you can kind of be you can be approximated by so you can kind of estimate how big this space is. So the gist of it is there's not that many matrices that would commute with something that's diffuse, and so that kind of underlies a lot of these properties. At least the basic versions here is that you know having too much commutation means you can't have that many matrix approximations. Okay, so with that first property in hand, well, let's consider the second property. So now if you have tensor product, so two, if you have tensor product here, then this is less than or equal to 0. And so here you could consider, well, let's say let A subset M2 be diffuse abelian. So then if you consider M1 tensor A, right, this the commutant of this contains A, and so it's diffuse. So H of M1 tensor A inside M1 tensor M2 is less than or equal to 0. But then you also consider that, and then actually maybe I say A2 here, right? And so then similarly, you can do the other way around. You can consider A1 tensor, you could consider A1 inside M1, which is diffuse abelian, and you can consider A1 tensor M2. And this will be less than or equal to 0. And then finally you say, well, A1 tensor M2 intersect M1 tensor A2 is diffuse, right? Because this equals A1 tensor A2. And so then you use the subadditivity property, and then that'll tell you the von Neumann algebra generated by both of these things together as H less than or equal to 0, which gives you what you want. Okay, so then there's more you can do with this, because, well, what if you aren't simply studying a tensor product? There's other situations where this could happen, such as graph product. So so a bit about graph products. So in the group case, graph product is sort of a mixture of free product and Cartesian product of groups. And so what does this mean? So you take a graph, right, and you've got vertices and edges. And so then the graph product, let's call the graph gamma, the graph product over the vertices of the graph of groups would be you take the free product of these groups, and then you quotient by the relations that the copies of GV and GW commute if the vertices are adjacent. And so when you take the graph product of groups, if you have two vertices that are not adjacent, then those two groups are in free position. And then if the vertices are adjacent, then they're in a direct product position. Right. So the long history of this. So this was defined by Edith Green. There's been also many papers analyzing the C-star algebra and von Neumann algebra analogs of this. And so in particular, you can consider graph product of von Neumann algebras with a state. And here we'll take a tracial state. And in that case, I mean, you have to specify what the state is. It gets a bit complicated, but in the group case, you know what it is. Okay, so what you can say about these graph products, right? So here's another proposition. So if gamma is a connected graph, and if you choose von Neumann algebras with trivial states for each vertex, which are diffuse, then the H of the graph product will be less than or equal to 0. And the reasoning for this is sort of taking this idea here, but kind of and using the subadditivity property and kind of chaining things together. Yeah, so by the way, this here proposition here is in joint work with a bunch of people, with me and Ben Hayes and Ian Charlesworth and Brent Nelson and Srivatsav Kunawalkam Eleavali and Rolando de Santiago. And we have this 6-person project studying many properties of graph products, right? And here's just one of them that basically doesn't have that many matrix approximations. So earlier, Ian Charlesworth and Benoit Collins gave a method of constructing random matrix models for these things. And it involved like looking at tensor products of several different things. But in terms of comparing to the ambient matrix algebra, those things lived on like much lower dimensional spaces. And so the random matrix models there that, despite having random matrix models, they don't give you an abundance of matrix approximations in the sense of this H, because they're living on lower dimensional spaces. Okay, and okay, well, let me prove this proposition. So let's consider M to be this graph product. Okay, and then let's consider yeah, so then for each vertex we have okay, and then let's say let me say this for W, which is a subset of the vertex set, let MW be the von Neumann algebra generated by the things in this set W, which is inside this M. So what we're going to do is a reason about right. So our goal, yes, we're going to show that H of MW in the presence of M equals 0. And we basically are going to do it by induction on the size of the W. So starting with two things, right? So yeah. And here, I guess we're going to have W here connected. So if we start with just two things, and if you have two things, right, then you have two vertices connected to each other. So that means that these two subalgebras here form a tensor product inside of the M, right? So this here is just going to be MV1 tensor MV2, and then that's going to be inside M. And I just told you tensor product has a H less than or equal to 0, right? So this works. And then, well, then you just want to go inductively. And so we're going to add on one vertex at a time, and just to make sure that you're adding on a vertex that's connected to the previous ones, right? So now take W, say union some other vertex V, and then what this V will be adjacent to some W that's in the original set W. And so then we consider that by the induction hypothesis, this is less than or equal to 0. And then also, if you were to take just these two vertices, this new vertex V that you're adding, and the vertex that it's adjacent to, you have a tensor product of those things. So this has entropy less than or equal to 0. And then you consider, well, MW intersects this tensor product is just going to be the algebra for that vertex, the vertex that your new one is connected to, right? So I guess maybe for a picture, right, you have this W, you have this lowercase w here, and your new vertex that you're adding on. And the intersection between the von Neumann algebras generated by these things and this thing will be the von Neumann algebra that's assigned to that vertex there. And that's diffuse. So the intersection is diffuse. We apply subadditivity, and so we get this as less than or equal to 0. Yeah, so by chaining together these properties with the commutants or normalizers of whatever, you can inductively show that these entropy will be 0. Yeah, so here, as usual, right? If you have something else that had a similar properties, then the same arguments would work. Yeah. So that's what happens with graph products. These basically all have this one bounded entropy 0, despite the fact that the graph products might have many features in common with free products. What happens though if you take your graph products, right? If I assume if I don't assume these are diffuse, for instance, what if I assumed I took finite dimensional algebras on the individual vertices? Then other things can happen. Like if your graph is a tree and you put a matrix algebra on each vertex, then using the work of Dykema on free products with amalgamation over finite dimensional things, you can show that this is going to produce an interpolated free group von Neumann algebra. And so this in particular will have H which is infinite. So you can get this to be infinite for some cases when you have finite dimensional things on the vertices. We don't fully understand under what circumstances this is true, but what we can say is if now let me erase this. If you have a graph product, and let's say for instance MV finite dimensional, and so then if the first L2 Betty number of the okay, so I don't know if you know about L2 Betty numbers or not. It's basically like some cohomology thing for groups that generalizes to algebras. And here I want to say that the Betty number of the tracial star algebra graph product. If this is 0,
What's the mean of V is equivalent to W?
I mean, that means adjacent in the graph. Adjacent.
Oh.
Yeah. Okay.
Not an equivalent to.
Yeah, that's not an equivalence relation. I'm sorry.
Okay.
I didn't invent this notation.
All right.
Well, it is not an equivalence rate, but it is a relation.
Oh, it's a relation, yeah.
Okay, anyway, so this is irrelevant, okay? This is irrelevant. Let's talk about the results. Well, I mean, your question, like clarifying questions are fine, but of course, we don't need to debate about notation. It is what it is. Anyway, so if the Betty number is 0, then also in this case, the H is 0. Is less than or equal to 0. So I'm not going to go into the proof of this because I want to get to some other stuff, but this is also a cool result. It uses so kind of one of the main ingredients is a result of Sliatenko, which is in general which is proved that for groups. So if the first L2 Betty number of a group is 0, then the group, then the group von Neumann algebra. Oh yeah, this is not actually. I actually don't know that it's less than or equal to 0, but I know it's less than infinity.
My recollection is that these beta is numbers are not invariants of the algebra, not known to be invariants of the algebra.
They're not known to be von Neumann algebra invariants, which is why I talked about the tracial star algebra.
Or you mean if you fix the trace, then they are. No.
The key point here is I'm not trying to take the von Neumann algebra. I'm not claiming that I have a von Neumann algebra cohomology. I'm just saying I take the star algebra generated by it.
Oh, okay, right, okay, good.
So without taking the completion. And for that, it makes sense to talk about L2 Betty numbers.
Okay.
So L2 Betty numbers are algebra invariant, but not von Neumann algebra invariant. Anyway, though, yeah. So such a result here uses the result of Sliatenko. Well, Sliatenko applied it to the group case, but basically the same machinery applies in a more general situation. But the interesting part in our paper is how to deal with sophicity. So Sliatenko's result uses sophicity of the group to do this, and so we had to come up with some sort of analog for algebras. And that I think can be its own talk, but this is just yes, I just wanted to mention this here. So it's another result about the H. And another situation that we know is from myself and Ben Hayes and Srivatsa Kunawalkam Eliavali, which unfortunately I will abbreviate. And that is that if M is a 2-1 factor with property T, then H is less than infinity.
By the way, I'm sorry I got him mixed up with, don't ask me why, with Caleb Decker. Because it worked, he's spelling it. I don't know why.
Oh, okay. Okay.
Okay, so he's spelling it out. Thank you.
Anyway, yeah, so these two are two non-trivial results here. So this result here, this first one, this also has like precursors in Jung's work, and then Sliatenko proved this version. Also, this one here about property T. So a weaker statement saying that it had a free entropy dimension at most 1 was proved by Jung and Sliatenko, and so then we have gotten to I guess the strongest version known so far, that if you have property T, then H is less than infinity. But in both of these instances here, we don't necessarily know whether it's equal to 0 or not. So this is a potential case where maybe there is something in here where it could be finite and positive, but we just don't know.
By positive, you mean non-zero? Or what? Well,
Yes.
no,
Yeah, so maybe it's
my positive includes 0.
Yeah, so maybe it's finite and non-zero.
Yeah.
Because looking at these, people have tried, like it doesn't seem like you can show that h equals to 0. Like at least not with any of those methods. Okay.
You will interpret the results again. So you write these inequalities. So you have. So what does it mean? So like you're saying that. So again, this inequality is again to me very confusing because you're just telling me that it's not infinite.
Right.
So what does that tell me? What does it tell me about the algebra? Or
Yeah, okay. So that's a good question. I think the most relevant information you can get out of this is kind of the interaction between things where it's infinite and the things where it's finite.
So again, infinite. So if I take it, so you were saying that if I take a free product, I would get infinity.
Yeah.
Right. If I have minus infinity, that corresponds to non-convertible things, right?
Yeah.
And then 0 maybe corresponds to something similar to amenability, sort of, maybe.
Yeah, only in a very weak sense. Yeah, so okay, so why do we care about showing it's finite? That's maybe the question, one question you want to address, okay? So it comes from, playing off the infinite case versus the finite case. So if you have, so like I said, if you have things with diffuse intersection, right, then you have subadditivity. So in particular, if you said, okay, well, as I said before, you can't take a free group von Neumann algebra and generate it with two amenable things that intersect diffusely. Okay, but now the same is true for property T, right? You take two things with property T that intersect diffusely, then they have to generate something where H is finite, so they couldn't generate a free product, for instance. Now and so in a sense, so the overarching plot is, things where the H is infinite cannot be decomposed and built out of things where the H is finite using any of these operations. And in terms of things where the H is infinite, free products are the main example that we know, but it's also true that that I guess with certain additional hypotheses, there's a sort of converse to this. That if the first L2 Betty number is strictly positive, that corresponds to like some kind of cocycles existing. And if you get these cocycles to exist, that actually take values in a group algebra instead of in the completion, then Shliak-Tenko has shown that then in that case, you can actually deduce that there will be generators with a free entropy dimension, which is bigger than 1. And so the H is infinite. Now, for many of these questions, you could ask, are there any examples known that are conclusively not free products? I mean, this is actually an open question in the group literature, like if the first L2 Betty number is positive, and are there any examples where it's not a free product? And so this is a big unknown. But certainly it's, there are other hypotheses that could be invoked other than simply being a free product, but would still get you H to be infinite. But a lot of them are things which are kind of a similar flavor to free products. I mean, you can also take free products with amalgamation over something amenable, and that works just as well as a plain free product. Yeah. Okay, so great. I have maybe like 15 minutes left. The other main thing I wanted to get to was getting somehow into what's the actual definition of the stage. So let me erase some space and start up. Okay, so as mentioned before, we have this space of laws for D tuples. Okay, so space of non-commutative laws for D tuples. Okay. And so then if you had given such a law, you could consider neighborhoods, right? You could consider O, which is a neighborhood in the space, and then you can and define your microstate space. So gamma n of O is tuples in matrices self-adjoint to the D, such that their non-commutative distribution is in the neighborhood O. Okay. So then when we define this H, the H for the say x1 through xd, you want to take you take this space. Yeah, we write it over here, yeah. Then you want to consider a covering number of it. So we consider a covering number. With respect to the 2 norm, right? The L2 norm corresponding to the trace. And when you take the covering number, right, it's you want to consider an epsilon covering number for a certain radius epsilon. So you figure out how many epsilon balls do you need to cover it. But then, as I mentioned before, if two things are conjugate by a fixed unitary, by a single unitary, then we consider them to be the same. So then this here is orbital, meaning this is considered modulo unitary conjugation. So that's the covering number that we consider. Well, then we consider logarithm of it and 1 over n squared, and then the soup as n goes to infinity.
Why is it n squared?
Yeah, so n squared has to do with the fact that the dimension of this space is d times n squared, right? So the n by n matrix is n squared dimensional, and so this is the natural choice of the normalization. Okay, so we have that. And then just as in the definition of the free entropy, you take the infimum over the neighborhoods O. But then there's another parameter here, which is this epsilon. So at the end, you take the sup over epsilon, like so. And there's various nice monotonicity properties of this, that for instance, if you make your epsilon smaller, then the covering number can only get larger. So taking the sup over epsilon is the same as taking the limit as epsilon goes to 0.
Is this related to degree or not?
Covering, no, I mean, this is not like a covering map in topology, right? This is like how many things do you need to cover the set.
Okay, covering dimension.
Yeah. I mean, covering dimension is based on such covering like this. But here, I mean, I don't care about the overlap. Well, okay.
Just so I understand, is it like a covering dimension or is it like a volume?
No, so it's just a covering number, right? So covering dimension would be like if I were to consider like how many of these balls overlap each other, right? But here I'm not considering any of that. I'm just saying how many balls do you need?
So it's like a volume, right?
It's not the same as volume.
But it approximates. My misunderstanding.
You could bound it above and below by the volume, but this is it ultimately gives you a different quantity, right? Because if you only were to look at the volume of it, okay, so if you took like the volume and divided by log epsilon or something, then this might be kind of comparable to that. But when you take the limits, it doesn't give you the same answer, right? It doesn't. So this doesn't give you the same answer as like such volume limits, which are like the definition of free entropy dimension. This is like a different quantity, but it's not. It's not a covering dimension per se, because you're not considering overlaps. Yeah.
There's something called Lebesgue, something like
Lebesgue number for a cover.
that. Oh.
Yeah. Anyway, so I mean, it's kind of similar to what happens in looking at dynamical entropy or Sophic entropy, because yeah, so say when you're studying, for instance, okay, here's another analogy, right, which is topological entropy. So topological entropy of an action And when you do that, what you're looking at is you look at basically how many like orbits of length n you can distinguish up to epsilon. And so in this case, instead of saying you look at orbit of length n, you say you look at n by n matrix approximation. But it's still like for each n, you're looking at somehow how many epsilon separated things there are. So that's kind of one way you can think of it as kind of similar to topological entropy. And then if you look at the case of like dynamical entropy and Sophic entropy, there's connections you can make there as well. Right. Yeah. So those are all good points of like how to think about this intuitively, like what kind of object it is. And the question, that you brought up of, well, what if you actually try to do a covering dimension of this instead of just looking at how many balls you need? I mean, that could be a useful quantity. Right? That could be useful for studying various things like this. Right. So it's definitely a good question to investigate. But at the moment here, this is simply how many balls do you need to cover it? You look like you have a question.
So this is what's dividing for.
Yeah, and so that's the theorem, right? That if you have two different generating sets, that you get the same answer. Now, I should also tell you what happens when you do it in the presence. Okay, so there's several, I guess there's several, there's several versions of the definition, and I presented you the simplest case first, right? Where you have a finite generating set, and you don't worry about it being in the presence of a larger algebra. Okay, but now let me consider this, right? So let's consider a to x1 to xd, and I don't know, in the presence of y1 to yk. So what do you do in this case? Well, here, then what you want to consider is you consider O, which is a neighborhood of the joint distribution of the x's and the y's. And so then you consider your microstate space for that, for the joint tuples x and y. But what we measure is just how many different values of x you get, not how many different values of y. So you want to take this thing, and then you want to like project it onto the x coordinates. And then you take your covering number. And then you take your logarithms and limits. Yeah, so this here represents, okay, this represents matrix approximations for x, which came from this space here where you consider joint approximations of x and y. And so this is exactly, matrix approximations for x such that there exists an extension to a matrix approximation for y. Yeah, and so this is how you define this entropy of this thing in the presence of this. So there's another wrinkle in here, which is, well, what if you do infinite tuple instead of finite tuple? And I don't have time to go into detail on this, but it works out just fine. Basically, instead of just picking an epsilon to do covering numbers, when you have your infinite tuple, you first you pick finitely many coordinates and then measure an epsilon of error in those finitely many coordinates. And so then you're replacing your parameter epsilon by the choice of a finite set of coordinates and an epsilon. And you do that, and then everything still goes through, definitions still make sense, and the proofs work in that setting. But let me stick for the finite case for now. Okay, so now I want to wrap up by giving a hint of like why this is actually an invariant. Okay, so and in fact, I mean, you could consider showing that it's an invariant and also showing the monotonicity properties at the same time. Right, and so for the invariance and the monotonicity properties, you would want to show a statement like this. that, so if you have W star of X contained inside W star of X prime, and W star of X prime and Y prime contained inside W star of X, Y, then this is less than or equal to this. So here, the X, Y, and X prime and Y prime are all tuples. They can each have different numbers of elements in the tuple. Okay, but so this one here, right, this shows the monotonicity property and the invariance at the same time, right? Because you know, if these are equal to each other, then you get the inequality in both directions, so you get the invariance. But then here, this is generally saying this is contained to this, so this is where you take the first subalgebra and enlarge it, and then here you take the second subalgebra and you shrink it. So this would contain all of them at once. And then the idea here for proving this is essentially you want to take microstate spaces. Yeah, so the idea here is basically like okay. First of all, you take X. X is like a function of X prime for some F. And I have to make sense of what such an F would be. But so if F was a polynomial, I mean, this kind of would make sense. Now, if X was actually in the algebra generated by X prime, then you could take F to be a polynomial and so forth. But the way that I do this is by using a more general type of function, which is some kind of completion of the space of polynomials, which is actually a very nice space because it enables you to express anything in the von Neumann algebra as a function of the generators. And then this function itself is something that makes sense to evaluate on any tuples from any tracial von Neumann algebra. But I don't have time to go into that in more detail. But then the idea here is that then you want to take the F, you want to take your function, and then you want to take like a microstate space for so here I want to take a microstate space for the O prime, and then I'm taking the projection onto the X's. And then I want to take this F and apply it to this microstate space, and then map this into the microstate space for the X. All right, so this one here is for X in the presence of Y, and this one here is for the X prime in the presence of Y prime. So if you can express your X as a function of X prime like this, then you could take that same function and apply it to all the matrix tuples in here. And so you're taking this function and using it to transform this set. And then there's basically two parts to the argument. One is to show that like the image of this transformation, the image of this thing is approximately contains this. And then the other part is to show that you can cover the image, you know, by you can pick some balls which cover this, and then apply F to the center points and get balls that cover the image. So, well, I'll just kind of sketch this here. So there's kind of two parts. So the point is, okay, so F is the F that I create is uniformly continuous with respect to 2 norm. And so then if you have some statement here like A minus B less than delta implies in 2 norm implies F of A minus F of B less than epsilon, then this would say that something like that if you have a delta covering of your microstate space for X prime, then you get an epsilon covering of, by applying the function f, you get an epsilon covering of the microstate space for x. Or sorry, an epsilon covering of the image of this. Right? You get an epsilon covering of the image. All right, so that's one part. And you can basically do this using the uniform continuity. And then the other part is to show that the microstate space for x is contained inside the neighborhood of some, say, I don't know, you do like some epsilon over 2 or something, and you say you want this to be in the neighborhood of the image of the other one. And so how do you achieve that? Well, you need to know that so basically you want to show that everything which is a microstate space, which is a matrix approximation for x in the presence of y, is close to f of something. All right, so the idea, okay, so the matrix approximation for x in the presence of y is close to some f of x, maybe f of xn prime, where this thing here is a matrix approximation for x prime in the presence of y prime. Well, and how do we know that? Well, okay. So how do we achieve that? Yeah, that the matrix approximations here are close to f of some matrix approximation for the others. Well, here we now use the fact that x prime and y prime can be expressed as a function of x and y. Yeah. All right, so this is true. You can choose this for some g, and so in particular, right, then x would be f of x prime, which would be f of the projection onto the first coordinates of g of x and y. And you can choose your neighborhood O small enough that this kind of f composed with pi x prime composed with g is kind of close to or maybe with xy is close to x. And so then when you do this, then you're going to say that well, your matrix approximation for x is going to be close to f composed with g of itself. And g of that thing is going to be in one of these matrix approximations for the x prime and y prime. So this is how you guarantee that actually taking this function and kind of apply it, taking the image of this other microstate space actually gets you everything in the first microstate space up to some epsilon over 2 error. So maybe this is a rough sketch, but hopefully you get the idea of this, of kind of, how having functions that have nice properties like this uniform continuity gives you a nice way to transform, kind of change coordinates in your generators. And this in turn gets you these invariance properties for this H. So this type of function, it's a a nice space that you construct. And it actually has a lot to do with tracial completions of C-star algebras, right? So the construction of this kind of, in a sense, can be realized as an example of a tracial completion. So the idea here is just, you want to take not just non-commutative polynomials, but you want to take a completion of them. And you want it to be flexible enough that it actually will give you, you're taking a completion with respect to a limit in 2 norm, but then you do it uniformly over the different non-commutative laws. But then you also allow scalar valued coefficients of your functions that kind of depend on the non-commutative law, which enables you to break down, kind of isolate parts of the space of non-commutative laws. So anyway, there's a whole construction of those functions, but the utility of these functions is exactly that. It has all these nice properties like continuity in L2, continuity with respect to of the law of f of x depends continuously on the law of x, and other properties like this. And these properties enable you to do things with this h. Okay, so I will end it there. You're welcome to ask more detail and talk with me later about it.
Can you give us a reference? Might be helpful to access to.
So let's see. So this proof itself has not been published yet, but the types of functions that are being used, and another application of kind of showing some properties invariant. This is in the paper with Hayes and myself and Brent Nelson and Thomas Sinclair, which is on the called a random matrix approach to absorption and free products. So this absorption in this paper is like the idea of absorbing amenability, right? So we talk about certain subalgebras, so inside of, so I guess the main result is, well, I guess it's a result that has been known before, but we give a different proof of it. It's essentially, if you have a free product and you have something which is amenable and intersects one of the things in the free product diffusely, then it actually is forced to be contained in there. So it's absorbed. Yeah, so we give an argument for this, which is based on the one bounded entropy and based on other aspects of random matrix theory.
What's that last word in the, you don't mean absorption?
Absorption, yes.
Okay, good. Now,
Absorption in the sense of if it intersects diffusely, then it's forced to be contained inside.